Hello, everyone.
Good evening.
Good evening.
I hope everybody's having as good a time as I am. Solving physics problems, preparing for class, all that good stuff.
Preparing for the test.
Yes. Yeah, don't forget your test is due Sunday night, so get her done. Everybody's coming in pretty quick tonight, so should be able to get started pretty soon. We'll finish up chapter 29 tonight. Now, may even go into chapter 30. Just keep rolling along. After chapter 30, I think that's where I take a break and go to, I can't remember if I go to quantum mechanics or if I go to some thermo or what. But anyways, I'll keep you posted. 30 is plenty long. We've got 30, which is basically inductance. So it's sort of like what we've been doing with capacitance and Gauss's law. Now we can use Ampere's law and create this thing called the inductance. And that also gets us into AC circuits, which is kind of cool. I won't do much with the AC circuits. I figure you guys that are going into double E will have plenty of classes on that. But it's nice to know you can always go back to this particular book if you need to. Then chapter 31 is basically going to Maxwell's equations and seeing how Maxwell fixed it to make it work, and seeing where waves come from, seeing what light is, all that cool stuff. And yeah, we skipped 32. That's all done via lab. So yeah, you might not have y'all done any labs yet with optics, like reflections and lenses and things of that sort?
Yeah. Yes.
Okay, cool. So yeah, that's what we do in our course in lieu of covering it in lecture. Is we cover it in lab, and we have two 3-hour lab sessions basically where you learn that. So you do get all the stuff that you get from a normal course, but we do a little bit more because this course is supposed to be a 3-semester course so that you can cover modern physics, but we can't offer a 3-semester course with a community college and get enough enrollment. So we try to get some of the modern physics in by doing relativity in the first semester and doing some quantum mechanics and nuclear in the second semester. So I guess this is about all that's coming for right now, so I might as well get started. Anybody have any questions before I do? I don't know why I pinned Maria's M up here, but I did. There I am. Whoa, my Lord, I've gotten big. I didn't mean to do full screen. All of a sudden, the whole screen is me. I'm like, ah. All right, so we'll go ahead and get started since it doesn't appear anybody has any questions. We sort of jumped around a little bit. We basically came out with Faraday's law, and that says the induced EMF is equal to the negative. If there happens to be multiple coils, is equal to the negative times n, the number of coils, times the derivative of the magnetic flux as a function of time. So that's what we were doing. We used that and talked about Lenz's law. That's sort of the concepts behind this stuff. Is you really got to know Lenz's law, how Lenz's law works, how to predict which direction a current will flow, all that good stuff. Then the other stuff's just pretty simple calculations, which I think you can see from the examples in the book. What's remaining, though, is some kind of neat stuff that I wanted to make sure I covered. So let me start off with sharing my screen. I've got the problems typed up again. So it says, consider a n equal 100 rectangular loop of wire. So in other words, I'm talking about not just a rectangular loop of wire, but a rectangular loop of wire that's repeated itself 100 times. With dimensions A equals 20.0 centimeters and B equals 15.0 centimeters. The loop spins at a fixed 60 cycles per second by its connection to a propeller and a steam tube and a centrifugal governor. So you might have seen these before in some old contraptions. There was a Wild Wild West type movie or something that Will Smith was in, where they had sort of that steampunk thing going on, where they had some old-timey devices. But basically, when you see like a ring of metal that's spinning and got little balls on it or something like that, basically when that tries to go too fast, the balls swing out too far and slow it down. And when it tries to go too slow, the balls go back in, and that makes it less force. So basically, by doing that, you can make a governor to sort of maintain that constant 60 cycles per second. So we're basically just spinning something at 60 cycles per second. That's also called 60 hertz, H-E-R-T-Z. So the loop spins at a fixed F equals 60.0 cycles per second by its connection to a propeller and in a steam tube and a centrifugal governor. It spins in a fairly uniform 100 Gauss magnetic field, so that once every cycle, the dA vector and the B vector are parallel, and once every cycle, the dA vector and B vector are anti-parallel. So that gives you sort of the orientation. I'll draw a picture. It'll make a little bit more sense in a second. You may assume, and this is me taking a lot of the difficult work out of it for you, you may assume that the dA vector would be dA times the cosine of 2 pi f times t I hat plus dA sine 2 pi f times t j hat. So basically 2 pi over the period, and frequency is 1 over the period, is really what you normally put in front of t when you're doing a wave function like this, or you're doing something where it's going to repeat in time. So by doing that, that just sets it to rotate at the right rate. So it literally will complete 1 circle every 60th of a second. So by sticking that 2 pi f in there, where f is the 60 hertz, you're guaranteeing that basically this needle, the sort of dA vector that points perpendicular to the plane of the loop, that will complete a 360-degree turn every 60th of a second. You can also assume that B is equal to B I hat. Again, I'm just trying to take some of the complicated work out of it for you. A, what is the magnetic flux as a function of time? Oh, excuse me. B, what is the electromotive force, i.e. the voltage as a function of time? C, assuming that the 100 loop rectangle has a total resistance of 1 kilo ohm, which probably is a little high, but still it's okay. What is the current as a function of time given that radius, or given that resistance? And D, is the voltage AC or DC? If it is AC, what is its peak voltage? And if it is DC, what is its voltage? Note, 1 Tesla is equal to 10 to the 4th Gauss. So a Gauss is roughly what the strength of the Earth's magnetic field is. I always forget whether it's a half a Gauss or it's a whole Gauss, but either way, it's roughly 10 to the 4th Gauss, or excuse me, 1 Gauss is roughly what the Earth's magnetic field is, whereas a Tesla is 10,000 times stronger. And typical MRI devices like you see in hospitals nowadays, if you've ever had an injury like to a knee or a shoulder or something, or if you've had more severe things that they had to check out inside of you, they'll often use an MRI. That thing usually runs from anywhere to 1 to I think 3 Tesla, just to give you a feel for that. So I'm going to write down all the data that I've been given. I've been given that N is equal to 100. I've been given that A is equal to 20.0 centimeters. B is equal to 15.0 centimeters. I've also got that F is equal to 60 hertz. I've got the magnetic field B is equal to 100 Gauss. I've got dA, which I already know, and I also know R is equal to 1 kilo ohm. I guess I could put the fact that 1 Tesla is equal to 10 to the 4th Gauss. But I know everything else, so I think that'll work just fine. Let's stop sharing the screen a second, and I'm going to turn it over to my document cam. So let me try to make some sense for you. What we said was we were going to treat our dA vector. I said my dA vector can be treated as dA times cosine 2 pi f times t times I hat plus dA sine 2 pi f times t j hat. Okay, so what that does is when t equals 0, I get cosine of 0 is 1. I get sine of 0 is 0. So the dA vector is going to point in the I hat direction. So what that means to us is this could be, for instance, the north end of a magnet, and this could be the south end of a magnet. You know, the north and south just have to be two north and south poles. It doesn't have to be the south pole of the other end of this one. You can still use the other one. That's what's going on here. So our magnetic field is actually going to point. Remember, magnetic fields act like old people. They leave the north and go into the south. So that's our idea that we're using here. So the magnetic field lines are pointing that way. Now what's currently going on is my loop of wire, which should be about the same size as this magnetic field band right here. Well, it has a dA vector that it equals 0 is parallel to the magnetic field. That, of course, is going to turn this way, and basically it's going to make 60 turns every second. So we're looking at the edge, and in fact, if I wanted to sort of draw this in 3 dimensions, I could sort of come back up and say it's doing this. There's my 100 turns back there. So that thing's spinning like that. Does everybody understand that now? Does that make some sense? And then I'm saying basically that the X direction is that way, and I'm saying that the Y direction is this way. So part A, they want us to calculate the magnetic flux. The magnetic flux is equal to the integral of B dot dA. If I take the advice that the problem gave me, which was, hey, use this for B and use this for dA, then I'll get the integral of B I hat dotted with dA cosine 2 pi F times T I hat plus dA sine 2 pi F times T J hat, like that. Of course, as I've told you numerous times, the dot product is a linear operator, so all these things that aren't vectors I can pull out in front of the dot product and just leave the, you know, I hats and J hats there. And you'll see, of course, I hat dot I hat is 1, but I hat dot J hat is 0, so only that term's going to exist, are going to survive. And in fact, the B and the cosine 2 pi F T is not playing any part in the integral. So I can go ahead and write B times cosine 2 pi F times T. All of that is just equal to the integral of dA, which the integral of dA, of course, is the area. And this thing is supposed to be, you know, A units by B units or whatever. So we're going to ultimately say that this is A times B times the magnitude of the magnetic field times the cosine of 2 pi F T. And that is the magnetic flux. Anybody have any questions on that? That makes sense, right? Not too difficult. So what we're imagining here is like there's a little shaft coming out of the center of this, and maybe it's going as the axle for a turbine of some sort. Basically, fan blades would work, right? And if you're pumping a constant amount of steam up there, that should turn it at the right rate if you've adjusted your propeller appropriately and all that good stuff, and your governor appropriately. It should continuously spin it. So you're basically converting, in that case, thermal energy of boiling water, which you could have boiled by burning coal, or you could have boiled by nuclear reactions, or you could have just had, instead of even having a steam turbine, you could have just had a windmill or a water mill. Either one of those would work fine too. As long as you're getting the sucker to spin, you're golden. So we've got that. Now part B wanted to know what the EMF was. And according to Faraday's law, E is equal to negative N d phi B over dt. So what I've got to do is take the derivative of all this with respect to time. That's easy peasy. I know the derivative of cosine is negative sine. So I'm going to say negative times a negative becomes a positive. I don't have to deal with that anymore. I'm going to say 2 pi F A B N B That's the whole string of constants that I just got from when you take the derivative of cosine with respect to u, you get negative sine of u, and then you got to take the derivative of u with respect to t, and you get 2 pi f. So that's where the 2 pi f came from. The AB was there, the B was there, and of course the n's in the formula. And now I've got sine of 2 pi f t. Okay. That is, in fact, our formula. Now, I'm going to go back and put numbers and all this stuff in a second, and that'll make it a little bit better. But this is our EMF induced. Okay, again, I can put all these numbers in here. I can put the 60 in here, and I'm going to, just like right now, I wanted you to see the formulas. I'll come back and write the numbers above them. Like, for instance, this 2 pi f is 360. You might as well say 367 because it's 76.990. So it's 377.00 like that. So it's really that close for the 2 pi f. The B, of course, is 10 to the negative 2 because basically you got to convert it to Tesla. It's 10 to the 2, and then you're going to divide it by 10 to the 4, so it'd be 10 to the negative 2. This would be 10 to the 2, so we got 1 there because n was 100. And then you got the times A and B, and then, of course, this 2 pi f right here is, again, 377.0. And that unit, by the way, just in case you're wondering, is radians per second. Okay. So now we'll actually, let me go ahead and do that part. I'll go ahead and say what E is so you can get some kind of sense of what it is. Does anybody know whether this looks like AC or DC? Direct current means basically there's a set amount of current. It doesn't really change. It might wobble a little bit just because it's not that perfect of a current producer, but basically it's never going to change direction or any crazy stuff like that. AC is alternating current, and it literally changes direction. Based on the voltage that we're seeing here, do you think this is going to be AC or DC?
Wouldn't it be AC?
Yes, it's going to be AC, and it's exactly what we expect AC to be. It's a sine wave. That's kind of the neat thing about it. So right now I'm going to go ahead and take that. We know that E is equal to all this stuff, and in terms of the numbers, when I multiply 2 times pi times f, I got 377.00 times A times B times N times big B. All of that gives me basically 11.31 volts times the sine of 377.00 radians per second times T. Now, if you wanted to actually do this, of course, you since I've got that in radians per second, you'd actually want to use radians for your trig function. But that's numerically what the answer is to part B. So if you look at a graph of the voltage, it would basically look, sine starts at 0. And of course, this thing started with the actual DA being parallel to B. So that would suggest that it's going to have 0 voltage initially. But as it rotates this way, okay, it's going to go through this process where it reaches a maximum, 0, a maximum the other direction, 0, a maximum the first direction, 0, a maximum the other direction, so on and so forth. So that's what the actual voltage as a function of time will be. And this number right here is 11.31 roughly volts. Okay. So y'all can see that yeah, that's very much what you think of when you think of AC voltage. By the way, this number just becomes, that one is just 300 times 10 to the negative 6 Tesla meters squared times the sine of 377 T. So that's it in numerical form. You can see, obviously, the magnitude here is 10 to the negative 6 times 300, which would be basically 0.0003. So that's what the magnetic flux. So that magnetic flux is not that big, but the big deal is it's then going to be multiplied by 100, and then it's going to be multiplied by 377. And because of all that, you ultimately get a nice voltage of 11.31 volts. Now, is that a big deal? Well, a car battery, when you're actually drawing current from it, usually isn't exactly on 12 volts. In fact, it's usually a little higher than 12 volts when you first get it. And when it's actually drawing voltage, it often drops down below 11.5, 11.2, stuff like that. So this is comparable to the voltage that you could get from any 12-volt battery. It's way more than enough to run your iPhone, for instance, or your Samsung phone or whatever phone you have. You could actually use this to charge it. But caution, caution, caution. Your iPhone's not supposed to be taking voltages that high. I'll tell you later about that. And two, it's not supposed to be taking AC. Okay. So that's something you got to think about. Now, part C is where we wanted to assume we knew the current. And when we have that current, we want to try to assume we knew the resistance, and we want to use that to calculate the current. So we know that according to Ohm's law, E, the electromotive force, is equal to I times R. So I is just the EMF over R. So basically, I get the same old rigmarole. I got 2 pi F A B times N times B over now the radius, or excuse me, the resistance, times the sine of 2 pi F T. Of course, numerically, this means we get a current of 11.31 milliamps. Notice I had to switch that to milliamps because I'm ultimately going to divide this whole thing that I got before that had 11.31 volts. I'm dividing it by 1,000, so that makes it a milliamp, times the sine of 377.0. Again, I can write radians per second, and radians is not a true unit. Remember, it's a pure number actually, so I can write that. That's basically the whole current as a function of time. So this is part C. Any questions on that? All right, and let's see what else I asked. So I think that was it, but let me double check. Is the voltage AC or DC? I think we already answered that. And if it is AC, what is its peak voltage? And if it is DC, what is its voltage? So we already basically did that. I will stop the share again. And basically for part D, our answer is going to be, it is AC, alternating current, and basically the peak. So I'll say like this. You usually do like that. Whoa, yeah, I can see that barely though. Or you'll say E peak is equal to 11.31 volts. So when you talk about your power coming into your house, they normally will say, oh, that's 110, or they'll call it 120 or something like that. And really it varies by that much. You can, read it at 110 or 120, but that is not the figure that's up here. Okay. The figure that actually is up there is the peak voltage coming to your house. And to give you some estimate, some idea what that is, if you take the peak voltage like here and divide it by the square root of 2, that would give me what's called the root mean square voltage. And that's the voltage that they're talking about when they say 120. So if I take 120 and multiply it by the square root of 2, I think you'll get like 170 is roughly what it is. If you do 110, you get about 155. So it's roughly 155 to 170 is the real peak voltage in AC stuff that comes to your house. Now, the big deal is this had this itty bitty 11.31 milliamps, which, by the way, a single milliamp can kill you if it's given to you in the appropriate way. Like if you put it across someone's heart or something like that, a single milliamp will kill you. So 11 of them will kill you 11 times. So don't think that that small amount of current means it's safe or anything like that. But the difference is when you're talking about the house voltage, when it comes in, yeah, it goes from 155 to 169 at peak, or 110 to 120 is the RMS. And that literally means calculating the square of this over one period and then taking the average of it, basically. When you take that average, that's called the root mean square. And it turns out it's just the peak value divided by the square root of 2. So that's where that number came from. But when you come talk about your house has a 200 amp supply coming to it, and in fact, it can pull more. It's just most houses are put in to install a 200 amp supply because that's all a house would need at any given time. But if you happen to be like Tesla was, he had at one point some 40,000 amps coming into his house because he was making Tesla coils and all sorts of crazy stuff like that. So I think that answers that question. Does anybody have any questions about how that worked out? Isn't it kind of interesting how easily you could make a electric generator yourself? Anytime you get something to rotate at a fairly uniform rate, you're going to get this current doing this. And in fact, if you did see how my loop has sort of one coil, if I did one coil and then did another at 120 degrees away, and then another at 120 degrees away, then notice I'm getting a 0 each time the dA vector lines up with the magnetic field. Well, that would be the case for each of those. So when this one's 120 degrees spun around that way, this other one comes in, it's reaching 0. And then when it spins another 120, then this other one comes around and it reaches 0. So you end up getting 3 currents like that, and they're each out of phase by 120 degrees. And turns out that's exactly how the electricity is brought into your house. It's called triphasic. Just by doing, instead of one loop, you do 3 sets of loops and have them offset by, like I said, 120 degrees. When you do that, then you can tap across 2 of them that are differ by 120, and that'll actually give you the peak voltage that they're dealing with. Like they talk about 37.2 in terms of electricity going across the poles, the top of the poles. That's 37,200. That's where that number comes from. So anyways, I will leave it at that. It doesn't seem like anyone has any questions on that. So let's turn to our next problem. Remember, I didn't actually show the numerical calculations. I had done them earlier just to make sure I didn't make any mistakes. You guys should do that. Should, multiply the 2, the pi, the f, the a, the b, in the proper units, of course, and all that stuff, just to make sure you can get the same number. But I'm pretty confident they're good. Here's number 2. It says, what type of current, AC or DC, is delivered by a USB port? How high is the voltage? What voltage and current charge an iPhone? What voltage and current charge an iPad? How can you possibly make your 120 volt, 60 hertz AC receptacle voltage charge your iPhone? So those are some pretty big questions, but they're mostly conceptual. So I wanted to give you an idea of how that actually works. I'm going to do save here since I found another typo. I'm going to stop share. So it turns out, let me kill this part right here. It turns out the little USB ports where you plug in your phone, for instance, for your computer to charge it, or where you plug in a mouse or even the little mouse radio so that it can connect to a wireless radio, that little thing runs roughly 5 volts. And when they say, 5 volts, that's the nominal voltage. So they normally pump out like 5.2, 5.3 or something like that. So that when it draws a current, it's still going to be roughly 5 volts. And it has a maximum for a USB. It has a maximum of about 0.5 amps. So half an amp, which again, that's 500 milliamps. And I told you a milliamp can kill you. So this can kill you 500 times as dead, right? So it's still not necessarily a safe electricity to deal with. But that being said, that is what the USB port supplies. And there's, sort of a universal agreement that this is what USB will be, okay? So all computer manufacturers have to meet that criteria that's going to be 5 volts and 0.5 amps. Now, when you actually plug in your iPhone or your smartphone, and they're pretty much all about the same in terms of voltage. I just happen to know the very specific details about iPhones and iPads because that's what I use. But when that's the case, and you plug it directly into a wall receptacle, you'll notice it's got this little plug that's got the two prongs that stab into the receptacle. Well, that is actually some solid state electronics in that little plug that actually convert the AC signal first into a DC. Well, first it actually reduces it by going through a transformer. And then by reducing it, after it reduces it, it takes that wiggle and cuts that out and makes it a DC instead of an AC. All that's done in that little box, which is pretty amazing. If you've ever made a AC transformer system like that, you'll notice that it's got a lot of stuff involved. So it's pretty impressive that they can do that with solid state electronics in such a small bit. But that's what they do. So they bring it down. It still reads about 5 volts. So they do step it down from 120, say, to 5 volts. A little different in there, the 120 to 5. Really what you're doing is you're trying to bring the peak down to 5. So I'll talk about that in a second. But when it comes out of the wire, that's supposed to deliver a whole amp of current. So that's a whole amp that you get. And that's why your phone will charge about twice as fast when you have it plugged into a receptacle as opposed to a USB port. If you ever plug in an iPad to an actual computer USB port, it'll normally say it's not even charging, and it expects basically 4 times as much current. It is charging. You got to turn it off completely and then plug it in, and it'll slowly charge, but it takes literally 4 times as long. And the reason being is because the current that's specified on a USB charger for an iPad is actually 2.1 amps instead of just 0.5 amps. So that's the big deal here. So now let me turn back the document and let you get some understanding of what I'm talking about. So wall voltage. So we're talking about your little receptacle that looks like this. That little receptacle has one long slit, and then it has a short slit, and it has a little mouth down here. Okay. When you wire this up, and I always have to check to make sure, so don't hold me on this, but generally speaking, I seem to recall the big one is the black wire, the little one is the white wire, and of course this one I know is the ground. So that's the way that works. And in fact, old timers, people that are sometimes a little bit more caring, will actually turn this upside down and mount it, especially in kids' rooms. The reason being is if this plug comes out, the plug's supposed to be completely sunk in there. If it comes out a little bit, then that little bit of metal is showing. Now, if it's set up like this way and gravity takes effect with, say, a paper clip and it lands on that side there, then that could be a problem because it's going to touch 2 probes and you're basically running black to white. Or if a child touches that across the top, they're going to get the crap kicked out of them. Whereas if you mount it on top, then the ground is the thing that would touch if the plug falls out. So a lot of times people will wire that upside down specifically for the purpose of making it a little bit safer for those that are involved. But again, I don't remember exactly whether this is the black one is the big one or the white one's the big one. Doesn't matter because it has the instructions literally written on the receptacle when you go to install it. The bigger point is out comes a VRMS. Again, that's root mean square, equal to approximately 120 volts. Okay, and that means a V peak on the order of, let's say, 156 to 170. So maybe the middle of that would be 7 above the 156. So that would be maybe 163. So let's just pretend it's actually fixed that the peak voltage is 163 volts. And that'll make our life nice and neat because it gives us one figure to sit out. But it's also 60 hertz, which means, of course, it's DC. So how do we possibly get this to run an iPhone? Well, an iPhone uses 5 volts DC at 1.0 amps. An iPad, on the other hand, uses 5 volts DC at 2.1 amps. So there's a neat way you can actually build a circuit, and I said PAB instead of PAD. There's a neat way you can build a circuit to actually make AC turn into DC, and that's called a full wave rectifier. So I'm going to now share my screen again, but this time I'm going to share it with this one so you can see what a full wave rectifier looks like. So with the full wave rectifier, which I think I put over here, here it is. Okay. Yeah. So this right here is an image of a full wave rectifier. Let me click on it. Let me explain to you how this works. So when you want to draw, instead of a battery, you want to draw an AC source, you generally draw a circle and then you put a little sine wave in it, and everybody understands that that is a AC circuit. Now I expected to have my video uploaded to YouTube before I got to class. That's not taking so long because it actually took longer. So that's kind of a problem. There's the image I'm looking for. So this is the little voltage source right here. And what that means is, like, for a 60th of a cycle or a 60th of a second, basically, actually it's a 1/20th of a second, this side's going to be positive. And then the next 1/20th of a second, 1/120th of a second, this side will be positive. So when this side is positive, it runs out this way, and these things, they literally look like they're only going to allow stuff to go from left to right, right? It doesn't look like it can go up that way, and that's exactly what it is. It's called a diode. And a diode basically it's got limits. It's got a certain amount of power it can deal with, and if you have too much power, it's going to burn it up. But as long as you stay below that power, then it acts like basically a one-way valve. So it only allows positive current, positive charges to flow this direction. It doesn't allow positive charges to flow this direction, as long as you keep it inside of its range. So when we picture conventional current, we picture the positive side having positive particles coming out this way, like protons or something, and the protons would actually be allowed to go this way. They're not allowed to go that way because that's a stop. So it, lo and behold, also can't go this way. So it goes right here to what you call the positive side. The negative side, on the other hand, which is basically where stuff gets sucked in. So the negative side is sort of sucking in positive charges. And now you can see the positive charges can come back here and go in that way. That's exactly what you want them to do, right? Now you switch to the next 101 over 120th of a second, and this side's positive and this side's negative. When this side's positive, what you see is the positive particles go this way. They can't go that way because that's a block, but they can go this way, which is again to the positive side. And the negative particles, which are trying to suck in negative stuff, well, they're coming in this way. And of course, now they're allowed to go that way. They could have been allowed to go this way, but since that's positive, it's not going to let it happen. Now they're going to go this way and go back here. So it's all like a regular battery, except when the battery has this side positive, then it goes through here, and the negative goes through basically, the negative goes through basically, here. Okay. And then the other half does it. So if you only had 2 of these diodes instead of 1, you'd be a half wave rectifier. But given that, let me stop for a second and show you what this does. So what this does, notice in each case, it took the positive and turned it into a positive. Then it took the negative and turned it also into a positive. So it took basically a voltage signal that looked like this, just like the one we just made with our little spinning loop. Okay. And the positive came through as the positive. And this will be like 163 volts. So it got to keep that. But then it turned the negative upside down, so it got to keep that. Then it turned the positive up the regular way, so it got to keep that. And then it turned the negative upside down, so it got to keep that as well. So if you just did that, then you'd get basically a signal that was 163 volts and would look like this. That's not very good, right? You don't really want that. So the first thing we're going to do is before we even run to that full wave rectifier, we're going to take this 163 volts and we're going to run it around remember the Pilgrim's belt buckle? We're going to run it around the Pilgrim's belt buckle such that this number of turns is lower than that number of turns. So maybe we'll say this number of turns is, let's say this number of turns is 360, just because that's a big number that multiplies everything. I want this to be a step-down transformer, okay? So this side's going to have a lot fewer turns because I want it to come out at 5 volts. So basically, I will take 360 and I will multiply that by 5, and then I'll multiply it by 100 or divide it by 163. And I will get basically 11 turns. So this side needs 11 turns. Where did I get that? Again, that is 5 volts, which is what I wanted, divided by 163 volts, which is what I had, times 360 equals approximately 11. Okay, maybe you keep it 12 because you're going to lose some energy to the diodes and all that good stuff. So now you've got a 5 volt signal instead of this 163. It's a 5 volt AC signal. You put that same full wave rectifier in there, and now you have a signal that looks like this. Right? But you can do that even better because, again, this is not really DC. It's a crappy, wobbly, bouncy version of voltage that runs between 0 and 5, basically 120 times every second. That might be okay for your circuit, but it's probably pretty crappy. So what they actually do is this. They add a little capacitor. We've learned about capacitors already. They'll add a little capacitor to it. And when you add a capacitor, that actually does something. Capacitors sort of slow down circuits. They make their voltage be reluctant to change. So I will show you. Here's one. So now if you put this capacitor here, what's going to happen is this positive still becomes positive and this negative still becomes negative or 0. But by setting this in here, it basically makes there be a time lag between the actual jumping up to 5 volts and dropping down to 0. So you ultimately get, when you use that, kill this again. So by adding that little, oh, I didn't mean to do that. By adding that little capacitor to the circuit, now we're taking this voltage right here, which I told you is kind of ugly. It's at least 5 volts, so that's kind of helpful. It goes like this, 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 this. So what this does is now it takes that and just slows the process down. So it comes back up, slows the process down, comes back up, slows the process down like that. So you get this little wiggle. It's still a 120 hertz wiggle, but the wiggle might be 0.2 volts, right? And if you set this up at like 5.2 or 5.3, as I suggested by using like 12 turns or 13 turns, then it won't matter because that wiggle will still be around 5 volts at the least. So that's how you actually could make your iPhone be able to be charged from your power. And that's exactly what that little plug does, believe it or not. That little itty bitty plug has a solid state circuit that first does this. It's got to do this first because you can't, if you make it a DC circuit first, or if you make it a full wave rectified thing first, it's a lot harder to drop it down with a transformer. You can't use a transformer to do it. You have to use something else. It's probably still called a transformer, but still you have to use something else. So that's how that actually works. Any questions on that? I know that's a lot of stuff. I just wanted to give you a little feel for what that is as opposed to just black boxing everything. If you have a laptop, you've probably seen the heavy little object that's in between your cord and your receptacle. That heavy object is literally doing the same thing. Most electronic devices run on DC, so they have to actually take the wall current and step it down to the appropriate voltage. And remember, voltages are always in multiples of 1.5 because, you know, a battery, a AA battery, a AAA battery, a C battery, all those batteries are 1.5 volts. And that's how they build batteries. They just stack 1.5 volt batteries on top of each other to make 3 volts or 6 volts or 9 volts or 12 volts. So by doing that over and over and over again, you basically get a certain voltage. So you can probably guess that your laptop computer is running on 12 volts. It might run on 15 because that's another 3 above, but generally 12 volts is a scenario. So they've got a step down transformer that takes it from 163 roughly peak voltage down to about 12 volts. And then they have a full wave rectifier that turns it into this wiggle like this, and then they've got basically a choke, a capacitance that slows it down and makes it into a ripple, and that's ultimately what comes through the little plug into the hole in the side of your laptop. Isn't that kind of cool? Any questions on that? Okay, so that was not quite as much of calculation. I mean, I did have to use basically the transformer equation to calculate the number of turns I needed to bring 163 AC peak voltage down to 5 volts. But other than that, it wasn't much calculation. It was more about the big concepts. Now, number 3, what is Faraday's law in integral form? Well, we found that Faraday's law, remember, is the electromotive force is equal to the negative 1 times n, the number of coils, times the instantaneous rate of change of the magnetic flux. So we want to put that in integral form, and that's what I'm going to do for you now is, and this will be number 3. So I'll stop sharing for a second. This is just going to be quick and dirty. Okay, what we learned earlier was that VAB, which is, VAB, which is just like electromotive force from A to B, is equal to the integral, negative integral of E dot dl from A to B. Remember we did that? So as you might have thought, if we actually had a closed loop, which is what we have when we actually do magnetic flux, you actually have a closed loop of wire. You got to compute all that all the way around. So this, which is in Faraday's law, is negative n d phi b over dt. You see that this is dealing with going around a whole loop of current. So instead of this integral, we're going to do a circle integral, get rid of the negative, and we get integral of E dot dl, which looks a lot like Ampere's law. See the E dot dl? Ampere's law is the closed integral of B dot dl. But with Ampere's law, it's mu 0 I. And here it's going to be n d phi b over dt. So that is, in fact, Faraday's law in integral form. And that teaches us something. That teaches us that we can get electric fields that look like magnetic fields. And remember, magnetic fields are like closed loops. They look like little circles and stuff, or ovals and junk like that. We can actually get circular electric fields and ovals and stuff just like a magnetic field. But our current now, the thing that acts like current, which was mu 0 times I enclosed, is now the change in magnetic flux. So the change in magnetic flux does the same thing as current did in Ampere's law. So if we just treat the left-hand side like Ampere's law, we can do the same sort of stuff we found before, only we just got to remember to use the change in magnetic flux for the current. So that brings us up to number 4. Does everybody sort of have some understanding of that? I know that's a high concept there, and you haven't really done any applications, so it shouldn't be that obvious to you what's going on, but the next example hopefully will show you. So now I'm going to do our last problem that I wrote up for tonight. It says use Faraday's law, like you do Ampere's law, to compute the electric field produced by 2 poles of an electromagnet whose increasing current is causing the magnetic field to change according to B of t equals B0 plus B slope times t. The B slope, I'm just meaning, hey, this is the slope of the B versus t curve. That's all I'm talking about there, okay? The radius of the circular magnetic poles is R, and I'd like to know basically what's the electric field computed inside of that. So there's not really a lot of symbols here, not a lot of data I need to take down. I can certainly remember all of it by the time I get back to the drawing pad and talking to you. But the bigger thing is you probably don't really know exactly what I'm talking about. So what I'm going to tell you instead is let's look from the side, and we imagine this is a ginormous north pole of an electromagnet. So in fact, what it would have is a series of wires wrapped around it like this so that it can make the north end of a magnet. And then very, very close to that is a south end of another magnet, which is again electromagnet. And they're basically driven by the same current just for efficiency purposes. Why would you want two separate currents to run through there when you can run both through here? And of course, pay twice as much electricity the other way. So this is what it looks like from the side. Now from above, so let's say looking from above, I'll just draw a little eyeball. Okay, looking from above, what I see is a magnetic field that's uniform going into the page like so. And what I'm saying is this distance from here to here is big R. And I'm saying that the magnetic field strength, which by the way, just like I showed you with the X's there, it's pointing downward. And it turns out B as a function of time is equal to some B0 plus B slope times T. And what I mean by that again is if I made a graph of B versus T, it would look like that. And this would be B slope. And this would be B0. Okay, that makes sense? So now treating this like an Amperian loop, okay, or like an Ampere's law problem, what you would do is you'd say, okay, well, I'm going to imagine an Amperian loop. In this case, I'll call it a Faraday'ian loop, if you will. And I'm going to imagine it rotating around this way because that's consistent with the magnetic field pointing into the page. Okay. So I'm going to make a hypothesis that E is equal to E of R in, say, the phi or in the theta hat direction. Okay. Now, in order to do that, what I'm basically sort of assuming is maybe I'm assuming this is the x-axis and this is the y-axis, and that works just fine for me. Okay. So E is going to be E of R times theta hat. I suspect it might depend on R, but I'm not really sure. And then, of course, DL has to be basically the radius out, which I'm just going to call little r. So DL is going to be little r d theta, and that's also going to point in the theta hat direction. Again, just using those theta hats from polar or cylindrical coordinates, just because you've seen them, and it's easy to say, right? So now I can say the left-hand side of Faraday's law. This was a Faraday'ian loop. So the left-hand side, closed integral of E dot dl is just going to be the integral of E of R theta hat dotted with R d theta theta hat. Again, this is a linear operator. The dot product's a linear operator, so I can bring the E of R, the R, and the d theta out in front of the theta hat dot theta hat, and we see theta hat dot theta hat is 1 times the cosine of 0. And since the integral is going to be over d theta, I get E of R times R are just constants. And that's E of R. It's not E multiplied by R there. This one's multiplied by R, but that's just E of R times d theta. And I'm going to integrate from theta equals 0 to 2 pi because that's 2 pi radians all the way around. Does that make sense to everyone? Looks just like Ampere's law. So in this case, I'm going to get E of R times 2 pi. That's the left-hand side. The right-hand side, on the other hand, is supposed to be, in this case, we only have one loop, so the n is irrelevant. So n equals 1, right? But d phi b over dt would be d by dt of the integral of b dot dA. Well, the whole reason this this North Pole and the South Pole of this magnetic field are so close to each other, or these magnets, excuse me, are so close to each other, so that the magnetic field will be uniform, and we're not going to get near the edges really. So in fact, you might even want to cut it to half the radius, but either way, it doesn't really matter. I'm going to actually just say it's going to be a uniform magnetic field, and because it's a uniform magnetic field, the B is basically a constant, and the dA is just basically a constant again. Specifically, the area is pi r squared, right? So I'm going to say d by dt of B of t times the integral of dA. That's really what you're computing here. The integral of dA, this part just becomes plain A, which is pi times, in our case, we wanted to go out to r, so it'll be pi r squared, right? Actually, I'll leave it as little r for right now. Sorry about that. I'll leave it as little r for right now because I'm only going out to that part, and we're going to try to stay within the total radius of this thing. So I'll just call it pi r squared for any r less than big R, because once we get close to r equal to big R, that's when we're going to start having fringing effects of the magnetic field going, say, like this a little bit and like this a little bit. And that's clearly not a uniform magnetic field. So now I can say left-hand side equals right-hand side. And when I set those two equal to each other, I get E of R times 2 pi R is equal to, now we're going to have this pi R squared. That's not going to change, so I can go ahead and put that out in front. But d by dt of B of t, since B of t was B0 plus B slope times t, I think you can see that the derivative of B of t with respect to t is just a slope. Does everybody agree with that? And notice, by the way, the slope does not have units of Gauss or Tesla. It's actually a Tesla per second, because it's literally a slope, which is rise, which is Tesla or Gauss or whatever, over run, which is seconds. So this is going to be B slope. So ultimately, what we have is we can cancel out one of the pi's, we can cancel out one of the r's, and we have E of R is equal to B slope times, I already canceled out the B, but I mean the pi, but I seem to have not put a mark on it, so kind of confusing me there, times R over 2. And of course, our hypothesis said that E was in the phi hat direction, or the theta hat direction, so that's our total answer. So that's kind of interesting. You can see that a Tesla meter per second times meter per second obviously has the same units as the electric field, which is volts per meter. So that's kind of interesting. Or more specifically, check this out. If you, let's say we take the volts per meter and divide it by the Tesla. So volts per meter, which is the unit of the electric field. If we divide that by the Tesla, we get meters per second. Isn't that interesting? So it turns out that the units of the electric field over the units of the magnetic field is actually equal to the units of the speed of light, which is just c. It's actually the units of any speed, but it turns out to be exactly equal to c. That is the relationship with this version of Maxwell's equations. That is the relationship that relates the electric field and the magnetic field. The electric field is b times the speed of light. So isn't that kind of interesting? Everybody knows where I got this from this, right? Y'all, could y'all see how I got this from this? Anybody miss that? Okay. All right, well, it looks like y'all did that pretty well. So you seem to be on a pretty good area of grasping that concept. Let me go ahead and go. That's the last of the examples. I hope you look at all the videos that are already posted for chapter 29. I've got a ton of those posted already on Canvas. They're actually just linked to actual YouTube videos that I made in previous semesters. But they're really good problems. You can check them out. You also notice that this problem is not unlike the one that Giancoli did at the end of his chapter. Yeah. Yep. So anyways, other than that, let's go ahead on and jump into chapter 29. So here's a neat thing that you'd normally learn if you took Faraday's, if you did the Faraday's lab, which is something cool that we do in our 242 and 202 lab courses. So it turns out that you can take a coil of wire like that, and you can jab, say, a very small magnet in there. And the instant you jab it in there, and only while it's moving, you'll get a current. So this actually will make a galvanometer go like the needle will swing one way as long as it's moving. Not only that, if you take and say, okay, now I've got this loop of wire, which I'm going to make really, really big for a reason. Right? And then you got this other loop of wire, which I'm going to make really, really small for a reason. And the two wires will come out separately over here like that. Now, if you jab this one inside of there, it turns out if this one's carrying a current, it'll make this one carry a current. And in fact, there's a relationship between those. The relationship basically is that the flux of one is essentially the flux of the other, sort of like that big rectangle problem I told you to learn in the first example in chapter 29. Wherever you have the magnetic field, that's got to hit the area and get a B times A, but where the magnetic field is 0, something else happens. So ultimately, what you find out is we're going to define something called the mutual inductance, M21. Now, the good news is the M21 means something very specific. So they'll say, we'll let phi21 be the magnetic flux in each loop of coil 2. So I could say maybe this is coil 2, the green one. Whoa, where'd my green marker? Oh, there it is. So this is coil 2. And of course, it has a number of turns into. And this is coil 1. And it has a number of turns in 1. So we're going to call phi21 the magnetic flux in each loop of coil 2 created by the current in coil 1. Okay? Then you can say that the magnetic induction induced in coil 2 due to coil 1, that's what this is right here, is actually going to be equal to N2, which is the number of turns here. Remember, you always multiply by the number of turns times your d phi dt times your phi21 over, lo and behold, the current that you have in object 1. So this one has a current I1 going in there. This one creates a current I2, say, there. So this thing called the mutual inductance is really just the ratio of the flux times the number of coils divided by the current. We also know, of course, that according to Faraday's law, the electromotive force in loop 2 is negative N2 times d phi 2 1 again over dt. So ultimately you can see that E2, if I plug in this, if I solve this phi 2 1 for this, I get basically M2 times I1 over N2. So I get M21, N2 is here. I'm going to take d by dt of phi 2 1. The phi 2 1, of course, is M21 times I1 over N2. And you see that the N2s will drop out, right? And you're left ultimately with just negative M21 di1 over dt. Now, if you do the same thing the other way around, you'll end up getting E1. In other words, now we're talking about what happens to the current in here, what kind of voltage is derived in here by this thing swallowing up that thing. Well, you can see from the symmetry of the argument, it's going to be the exact same thing, except instead of M21, it's going to be M12. So this is M21, this is going to be M12, and it's going to be, in fact, di2 over dt. Now, it turns out theoretically that M is what we're going to call M12, but it's also what we're going to call M21, because it turns out that M21 and M12 are exactly equal. And it's going to be called the mutual inductance. And the only problem you'd ever really do with this is exactly problem 30, example 30-1, where it says, a long, thin solenoid of length L, cross-sectional area A, contains N1 closely packed turns of wire wrapped around an insulated coil of N2 turns, see figure 30-2. Assume all the flux from coil 1, the solenoid, passes through coil 2 and calculate the mutual inductance. So I will leave you to look at that. It's really straightforward. So read example 30-1 and know it. And the reason why is because I don't do anything with mutual inductance except occasionally I literally use that same problem. So make sure you can do this. Make sure you sort of understand the ins and outs of it, okay? Flux in general, when the magnetic field isn't changing and when the area is not changing, flux is just BA. So you can immediately calculate what the flux is. Well, it's BA, but we also found out that the flux could be related to N1 and N2 and all that good stuff. And lo and behold, when you put these definitions of mutual inductance, the number of turns of the first one times the flux through the second one divided by the number of turns, the number of the current of the second one, that gives you what you need to know. And you can actually find that the M, the mutual inductance, is mu0 N1 N2 A over L. So that's basically it. That's the whole reason, though, that I wanted to show you that mutual inductance is there's something called self-inductance that looks a lot like mutual inductance. So this is mutual inductance. And it's important, don't get me wrong, it's very important. In fact, if you've seen some of the new iPhones and various other electronic devices that you can just lay on a surface and it will actually charge, that's how it charges, is through this inductive process. It basically creates a current carrying loop that creates a magnetic field. That magnetic field goes through the current carrying or the potentially current carrying loop in the back of the phone or electronic device. That generates a current in that loop. that current can then be used to charge the battery. So this mutual inductance stuff is super, super important from an engineering and science standpoint. But the stuff that we use in electronics is mostly self-inductance. And self-inductance are just called inductance, is given the symbol L, and it's measured in henries. Okay, that's a neat little unit. But just like up here, it was N times phi over I. Guess what? It's N times the magnetic flux over I. That's it. Because of that, we now have a new expression that can go into like a Kirchhoff's law. Remember, Kirchhoff's voltage rule said the sum of the voltage drops and increases around any closed circuit has to be equal to 0. Well, because of this, which ultimately allows us this, we now know that a voltage drop or increase, depending on how you're looking at it, is negative L di dt, just from that equation. So this is another term when we start to use equations and we need to go around, just like before, we could say Q is equal to V over C. Well, now we can say E is also equal to negative L di dt, and that's another term that changes a voltage. So C equals Q over V basically gave us V equals Q over C, which we could use to recognize the change in voltage and going across a capacitor. Now I can see that the change in voltage upon going across a inductor is L di dt. How do you calculate that? Well, that's kind of cool because it turns out most of them are just solenoids, some of them are toroids, but you basically calculate the magnetic flux. You use Ampere's law to calculate B. Then you do the integral of B dot dA for the area of the end here, not like some other area. I'm talking about the little circle end here. You use the integral of B dot dA, and that gives you the flux. And then you take that flux and you divide it by the current, which, remember, Ampere's law gives you the magnetic field in terms of the current. So this will actually get rid of the current. And lo and behold, you now have the inductance or self-inductance of the object. So that's the whole thing that we're going now. So it's almost like we've gone, since we're near the end, it's almost like we've gone full circle, or I shouldn't say full circle. We've gone through a cycle. So we learned about electric force using Coulomb's law. Then we learned about the electric field that allow us to explain the action at a distance. How is this force being applied to something some distance away without physically touching it? Then we were able to use that to compute, basically with Gauss's law, we were able to compute the electric field as opposed to just the force field. The electric field, which is what would allow us to bypass that action at a distance thing. But we could use Gauss's law to calculate the electric field, and then we could say, well, C equals Q over V. So if I take that Q in this particular voltage arrangement and divide it by that voltage that I just calculated using V equals negative integral E dot dL, then I was able to get the capacitance of this physical device. Well, now we've taken and gone a step further, and we introduced the law of Biosavart, which gave the magnetic field. But we found that that was really ugly and would require us to use a lot of computer time if we really wanted to calculate magnetic fields that way. So we tried to only calculate magnetic fields for very symmetric objects. And those very symmetric objects lended themselves easily to Ampere's law. So we use Ampere's law to compute the magnetic field. Then we use flux equals the integral of B dot dA to calculate the flux. We divide that by the current, and then lo and behold, we get, and multiply it by the number of turns if you got that. But lo and behold, you now have an inductance, which again is a physical property of an object. So those are two very similar parallels, and they're sort of the holy grail of this second semester E&M part of the course. If you can go through that, 4-step process from computing electric field to getting capacitance, and from computing a magnetic field to getting inductance, then you've probably knocked out 70% of the course material for this course, at least for the 80% for the electric part. So any questions on that? That's what we'll finish up next time, is actually using Ampere's law and the integral of B dot dA to compute actual inductances. You can look ahead. You can look at my videos that I've already posted. That should get you somewhere. But the time is actually essentially up. So feel free to stick around, ask me questions. I'll wait for the last person to leave. Don't forget you got a test due Sunday. Get that done. And don't get too behind on this trying to do that. So you still got to, you know, do 2 or 3 things at once.
Thank you, Professor. Have a great night.
You too. Thank you, Sean. How's it going, Jamie? You're not as vocal and active as you were last semester.
I'm fine.
You okay? This material is very different, man. It's it can be, one is normally really intimidating. It's not that much harder. It seems a lot harder, but it is very intimidating. So a lot of people sort of don't get it or feel like they don't get it until the very end. If you can solve the problems, though, you're in a good spot. That's the main thing. Just keep solving problems and being able to get right answers, and you're going to ultimately figure it out. Not to say I'm not basing that on any knowledge of your grades. I'm just trying to, you know, tell everybody, hey, this seems hard, and that seems like a steamroller, me coming in here and blowing you away with these problems, but you probably feel like everybody else.
All right.
How about you, Benjamin? You have any questions?
No.
And you don't either, Brittany. All right. Well, y'all have a good one, guys. Get your test done. Have a nice weekend.